How are offshore wind farms built? Step by step explained. Offshore wind farm construction is a complex process involving multiple stakeholders, advanced technologies, and significant environmental considerations. As demand for renewable energy grows, offshore wind is becoming increasingly important due to stronger and more consistent wind conditions at sea. This leads to high operational complexity. Building large-scale offshore wind facilities requires specialized engineering, precise logistics, and coordinated planning across all project phases, often under challenging marine conditions. A range of risks and uncertainties must also be managed. Technical challenges, environmental factors, and coordination between stakeholders all affect execution and timelines. As a result, offshore wind construction relies on structured phases, clearly defined roles, and careful risk management to ensure successful delivery and long-term performance. The construction of an offshore wind farm begins with a detailed feasibility study and site selection process, forming the foundation for all subsequent phases. This stage evaluates wind resources, environmental impact, and economic viability to determine whether a project can proceed. A key part of this process is wind assessment. Technologies such as weather towers, LiDAR systems, and satellite data are used to analyze wind speed, variability, and extreme conditions. Offshore locations with stronger and more consistent winds are often preferred for large-scale development. This analysis leads to environmental evaluation. Impact assessments examine potential effects on marine ecosystems, including fish, seabirds, and marine mammals, as well as factors like construction noise, water flow changes, and electromagnetic fields from cables. This allows mitigation strategies to be developed early. Stakeholder involvement is also essential. Environmental experts, regulators, and local communities contribute to the process, ensuring that ecological and social considerations are addressed. Economic viability must then be confirmed. High capital requirements require careful evaluation of costs, expected energy output, maintenance, and projected revenues. Financial support often involves collaboration between investors, banks, and governments, with mechanisms such as subsidies or price guarantees helping to reduce risk. In this way, feasibility studies and site selection ensure that offshore wind projects are technically, environmentally, and economically viable before construction begins. Once a site is confirmed and financing secured, the design and engineering phase defines how the offshore wind farm will be built and operated. This stage brings together technical specifications, logistics, and safety requirements into a detailed project plan. A key decision is turbine selection. Size, rotor diameter, and capacity are adapted to site-specific wind conditions, with larger turbines often preferred offshore. This, however, adds complexity in transport, installation, and maintenance, requiring designs that can withstand harsh marine conditions and corrosion. This leads to foundation design. Structures must support large turbines under constant exposure to waves and wind. Monopiles are common in shallow waters, while deeper sites require jacket structures or floating platforms, with seabed conditions guiding these choices. Electrical infrastructure is then developed to transmit power efficiently. Inter-array cables connect turbines to offshore substations, where voltage is increased before export cables carry electricity to shore. Design must consider distance, seabed conditions, and external risks, such as shipping routes. As a result, the design and engineering phase creates the technical backbone of the project, ensuring all components work together efficiently in a demanding offshore environment. The procurement and manufacturing phase secures all components needed for offshore wind farm construction, including turbines, foundations, electrical systems, vessels, and specialized installation equipment. This stage turns design plans into physical assets, ensuring readiness for offshore deployment. A key focus is turbine manufacturing. Offshore units are built to withstand harsh marine conditions, with blades, nacelles, and towers produced to strict standards. Large-scale production adds complexity, as blades can reach lengths of up to 100 meters, requiring rigorous quality control. This leads to logistical coordination, transporting oversized components from factories to ports, and then offshore requires careful planning, using specialized vessels such as jack-up ships and crane barges. Scheduling is also critical. Projects rely on tightly managed timelines that consider weather, port capacity, and vessel availability, as disruptions can cause delays and increased costs. As a result, procurement and manufacturing are a pivotal stage, ensuring all components are produced, delivered, and ready for installation with precision and efficiency. Installation and construction at sea represent the most complex phase of offshore wind development, bringing together marine contractors, turbine installers, engineers, and safety specialists in a tightly coordinated process. The sequence begins with foundation installation. Specialized jack-up vessels position structures on the seabed using pile driving for monopiles or more complex methods for jacket and floating foundations. Precision is critical for long-term stability, while noise reduction measures help limit environmental impact. This is followed by turbine assembly. Tower sections, nacelles, and blades are transported offshore and installed using heavy lift cranes. Blade installation is particularly sensitive, requiring calm weather and careful coordination. Electrical infrastructure is then deployed. Inter-array cables connect turbines to offshore substations, while export cables carry power to shore, laid and protected on the seabed using specialized vessels. As a result, this phase depends on precise execution, suitable weather windows, and close collaboration to ensure safe and efficient project delivery in challenging offshore conditions. Once installation is complete, the project moves into commissioning and testing, ensuring all systems operate correctly before power generation begins. This phase validates the performance and reliability of turbines, electrical infrastructure, and control systems. The process starts with electrical system commissioning, inter-array and export cables, offshore substations, and grid connections are tested to confirm proper integration and stable voltage levels, as faults at this stage can cause delays and risks. This leads to turbine activation. After approval, turbines are energized and tested for startup and shutdown behavior, response to wind conditions, and overall energy output. Control systems are then evaluated. Automated systems that adjust turbine orientation and rotation speed are tested to ensure efficiency and safe operation. As a result, commissioning ensures all components function as intended, allowing the wind farm to move into reliable and efficient power generation. Once operational, an offshore wind farm enters the operation and maintenance phase, where sustained performance depends on continuous monitoring and regular upkeep. Although turbines are designed for automated operation, ongoing maintenance is essential to ensure efficiency and safety. Routine activities include inspections of turbines, foundations, and electrical systems to detect wear or emerging issues. Access is typically provided by vessels or helicopters, with tasks such as blade cleaning, lubrication, and software updates carried out under controlled conditions. This requires careful logistical coordination. Maintenance schedules must account for weather constraints, as rough seas and high winds can limit access and delay work. Unplanned maintenance adds further complexity. Mechanical failures may require specialized vessels and equipment, increasing costs and causing temporary production losses. As a result, operators rely on remote monitoring systems to track performance in real time, enabling early fault detection, reducing downtime, and maintaining consistent energy output. Offshore wind farm construction, despite increasing standardization, remains exposed to a range of uncertainties and hazards that can affect timelines and project outcomes. Weather conditions are the most significant source of uncertainty. Storms, high winds, and rough seas can delay installation, damage equipment, and in extreme cases, cause structural impacts. While forecasting helps identify suitable windows, unpredictable conditions remain a constant challenge. This connects directly to regulatory and environmental complexity. Changes in regulations, Stakeholder concerns or environmental findings, such as protected species, can delay or alter projects, making early engagement with authorities essential. Supply chain dependencies add further risk. Projects rely on global logistics for turbines, vessels, and equipment, so manufacturing delays, labor shortages, or transport disruptions can significantly affect schedules. As a result, operational safety is critical. Offshore construction involves risks such as falls, equipment failure, and harsh conditions, requiring strict procedures, specialized training, and strong emergency preparedness to protect personnel and ensure safe execution. In this way, offshore wind development depends on managing environmental, logistical, and operational risks to achieve successful and timely completion. Offshore wind farm construction is a complex, multidisciplinary process involving developers, manufacturers, environmental specialists, and regulatory authorities. Each phase, from feasibility and design to installation and operation, introduces challenges and risks that must be carefully managed. This complexity highlights the importance of coordination. Successful delivery depends on aligning technical, environmental, and regulatory requirements across all stages. At the same time, the strategic value of offshore wind is clear. Access to strong and consistent winds at sea enables large-scale generation of clean electricity, supporting global energy transition goals. As a result, continued technological progress and industry experience are expected to reduce challenges, improve efficiency, and expand opportunities for offshore wind development.